All right, today we're going to again talk about systems of linear equations. These are the notes that we took on yesterday. We talked about the definition of a system of linear equations, system meaning more than one. So this is where you have more than one equation. In this course, you're going to solve two equations at a time, okay? So your system is only going to consist of two equations. When you get to other courses, you may have three and four equations, all right? In this equation, in a system of equation, your x, and we talked about it, but we didn't write it down, your x in both equations have the same meaning. Your y in both equations have the same meaning. So if your x in one equation is going to be the number of hours, it is also going to be the number of hours in the other equation, okay? If your Y is the total income, then your Y is going to be total income in both of the equations within that system. So that's very important to remember that the X's have the same meaning and the Y's have the same meaning within the system. These are some characteristics, some other characteristics that we talked about. The solution to a system is going to be the points that the equations share. It's the point that the equations share, okay? All of the points that they share. There are three possible solutions. If you graph the linear equations and they don't touch each other, which means they're parallel, going in either direction, it's a no solution. If you graph them and they intersect, the point in which they intersect is going to be the solution. If you graph the equations and the equations happen to be right on top of each other like this right here, they have an infinite number of solutions because they have an infinite number of points that they share. They share all of the same points. Some vocabulary words or some descriptive words that you use to describe a system is consistent. Consistent you use when the lines touch each other. They could be right on top of each other or they could cross in one place, but you say that they are consistent when they touch. If they don't touch each other, it is inconsistent. Those are vocabulary words that you use. All right. Then we have independent and dependent, only for consistent systems, which means they touch. If they touch in one place, that means they have one solution. That is independent. One solution is independent. If they have infinitely many solutions, it's dependent. They're right on top of each other. They're dependent on each other. Okay? They're right on top of each other. All right, and then we wrote this graphic organizer here. And down here, these are the different types of solutions where you have one solution, they cross at one point. No solution means they don't cross at all. And infinitely many means they graph the same exact line. Any questions about the notes that we took on yesterday? All right. Then on yesterday, we solved the system of linear equations by using the graphing method. Okay, we use the graphing method to solve a system of equations. And I wrote that up here. When you're using the graphing method, that means you're going to graph both of the equations to figure out what points they actually share. When you graph, an equation must be written in slope-intercept form. That's y equals mx plus b. And that's what we did in these examples. We graphed both equations. And if the equations were right on top of each other, just like in this example, the answer is infinitely many solution. And we gave it description words. We described it as being consistent because they touch. Dependent because they're right on top of each other and they share all of the same points. Okay. So now let's do number 2, or I'm going to show you how to do number 2. Now I'm going to go through this a little bit faster than I would if it was the first time, because this one you should have already done. Nonetheless, if you need me to slow it down because you don't understand something, then you just need to tell me that. Ms. Reyes, could you please slow that down a little bit? All right. So first thing that we're going to do here, just as we did in the example above, is we're going to write each of these equations in slope-intercept form. That's y equals mx plus b. So we have this equation right here, x minus 2y is equal to 4. We have this equation here, x minus 2y is equal to a negative 2. So to write this in y equals mx plus b form, to get y by itself, we're going to get rid of the x first. Okay? So when we subtract x, this is going to give me a negative 2y on this side. On this side, these are not like terms, so I bring them both down. Okay? Lastly, to get y by itself, I'm going to divide everything by that negative 2. Okay? So this gives me y is equal to negative divided by negative is a positive 1/2 then x. A positive divided by a negative is a negative. 4 divided by 2 is 2. Okay? So this is the equation here. My m is 1, 2. This is my rise. This is my run. My b is negative 2. Okay? All right. I'm going to go ahead and write this in slope-intercept form by again moving that x. So I'm going to subtract. I press down too hard on my pencils. That's why they're always breaking. Sorry about that, y'all. You subtract x on both sides. This is gone, and I'm left with negative 2y is equal to, on this side, these terms are not alike, so I'm going to bring them both down. Doesn't matter which one I write first. I'm just going to write the x term first because that's what I'm used to doing. Now I'm going to divide everything by this negative 2 because remember, in order to get rid of this negative 2, which is being multiplied, the opposite of multiplication is division. So you're going to divide each of these terms by negative 2. This is going to give me 1y on this side. A negative divided by a negative is a positive. This gives me a positive 1/2 x. A negative divided by a negative gives me a positive 1 here. Okay? So my slope for this one I notice is the same as my slope here. 1/2. This is my rise. This is my run. My y-intercept is different though. My y-intercept is 1. Okay? What I know about equations that have the same slope is that they're going to be parallel. So already I know they're not going to touch each other at all. Okay? So this is going to be a no solution. So I'm going to go ahead and graph them. To graph, I find negative 2 on the y-axis. You see, this is the y-axis here. Sometimes these graphs look so confusing. So negative 2 from the origin is down 1, 2. So I'm going to put my point here. This is where I start. Okay. I use my rise over my run. My top number is a positive 1, so go up 1. My bottom number is a positive 2, so go to the right 1, 2. So that's up 1, right 1, 2. Up 1 and to the right 1, 2. Up 1 and to the right 1, 2. Up 1, right 1, 2. Go until you run out of space and point points in the opposite direction. Instead of going up 1, go down 1. Instead of going to the right 2, go to the left 1, 2. So that's down 1 to the left 1, 2. And you follow that pattern. Down 1 to the left 1, 2. Down 1 to the left 1, 2. Down 1 and to the left 1, 2. Okay, you're going to connect these ordered pairs. Make sure that you extend your line and draw arrows at the end. Okay. The second equation, your b, your y-intercept is at 1. This is my y-axis here. So my origin is right here. Positive 1 is up 1 from the origin. Okay. I'm going to use the same rise over run. Go up 1 to the left. To the right. 1, 2. Sorry, y'all. Up 1, right 2. Up 1, right 2. And so on and so forth. Okay. If you want points in the opposite direction, instead of going up 1, go down 1. Instead of going to the right 2, go to the left 1, 2. Down 1 and left 1, 2. Down 1, left 1, 2. down 1 and left, 1, 2, down 1 and to the left, 1, 2. Make sure you connect the ordered pairs. Extend your line and put arrows at the end. Okay? Remember, a system, the solution to a system is all the points that they share. If they don't touch each other, they don't share anything. So the answer to this one is a no solution. Okay? Now, if I want to use descriptive words for this, what type of description could I give this? Would I give it consistent or inconsistent? Anybody? Would I say, very good, it is inconsistent. Good job. Okay. And that's all you would say about this one. It's inconsistent, and of course you know it's parallel. Okay. All right, so now we're going to do number 3. My number 3 is chopped off, so I'm going to use a separate piece of paper. Your number 3 is in good condition. Mine is chopped off. So I'm going to rewrite it on this piece of paper here. We have x plus y is equal to 2, and then y is equal to 4x plus 7. I poked a hole in the paper. All right, so this is my system. Let me use this as cushion. This is my system. So to solve this system, I have to write both equations in slope-intercept form. Okay, one is already written. This second equation is already written in slope-intercept form. So that's less work. M here is 4. Put a 1 under it. This is my rise. This is my run. B here is 7. Okay, it's already written in slope-intercept form. This one, to write it in slope-intercept form, I got to get y by itself. So I'm going to subtract x on both sides. So this gives me y is equal to, these terms are not alike, bring them both down. That's negative x plus 2. Okay? All right, so m here, the number that's automatically in front of this x is 1. Since it's a negative there, then it's going to be a negative 1. To make it a fraction, I put negative 1 over 1. So this is my rise, this is my run, and my b is 2. Okay? So now I'm going to graph. Now it's out the way. So when I graph this, I'm going to find 2 on this y-axis. This is the origin. So 2 on the y-axis is up, 1, 2. Rise is negative 1, down 1, and to the right 1. Down 1, right 1. Continue that same pattern until you run out of space. You want points in the opposite direction. Instead of going down 1, go up 1. Instead of going to the right 1, go to the left 1. So it's up 1, left 1. And continue that pattern until you run out of space. Connect the ordered pairs. Okay. All right. The second equation, you're going to start 7 on the y-axis. 7 on the y-axis is up 7 times. 1, 2, 3, 4, 5, 6, 7. Okay. And now from here, you're going to use the slope. So that's up 4. 1, 2, 3. Look, there's not enough space, okay? So let's put points in the opposite direction. Instead of going up 4, go down 1, 2, 3, 4, right here. Instead of going to the right 1 like you would have done, you go to the left 1 because you got points going in the opposite direction. So left 1 is right here. So down 1, 2, 3, 4, left 1. 1, 2, 3, 4, left 1. 1, 2, 3, 4, left 1. Okay? Connect. Okay? Here, the solution is going to be this point right here. This is the only point that they share. So if I start at the origin, I went to the left 1 time. So it's going to be -1, and then I go up 1, 2, 3. So it's -1 and +3 as the ordered pair. This is going to be the solution. Okay. How would I describe this system? Do I say it's consistent or it's inconsistent? Anybody? How would I describe it? It would be consistent. Good job. Would it be independent or dependent? Anybody? Independent or dependent? Pause real quickly. It would be independent. All right, I'm going to pause. Okay, so now we're going to use the substitution method. I'm going to put method right under substitution because this is what it's called. We use the graphing method to solve a system, which means to figure out what points do they share. Now we're using the substitution method to figure out what points these equations share. So the substitution method is a method used to solve a system. It's too big. A system of linear equations by using algebraic methods. Okay. And I'll pause to give you a chance to write, okay? Okay. When you are using the substitution method, automatically assume that the ordered pairs cross, okay? That these lines cross, sorry, I said ordered pairs. Automatically assume that these lines are going to cross each other. So if they cross each other, then you have one ordered pair as the solution. If you'll know that it doesn't cross each other when you start using the algebraic properties or solving equations and the variables cancel out. If, and I'm going to write this up here, if variables cancel out, this is a kind of a helpful thing. If variables cancel out and both sides are equal to each other, like you might have 3 is equal to 3, okay, variables cancel out, you might at the end, you see both sides are equal to each other, then you're going to say, oh, this is infinitely many solutions. Okay? If the variables cancel out, if, let's just say variables, if variables cancel out and both sides are not equal, like maybe 5 is equal to 7. 5 is not equal to 7. Then that means this system has no solution at all. Okay? This is going to be super important, right, to know. This is going to be super important to know because you are going to have problems that when you substitute values in, the variables are going to cancel out. And then when you get down to the end, you notice that, oh, both sides are equal to each other. That's infinitely many. Or, oh, both sides are not even equal to each other. That's a no solution. So that's how you know whether it's one solution, because it's going to work out perfectly, infinitely many solutions, because the variables cancel out and both sides are going to be equal, or no solution, when the variables cancel out and the answers are different. It's not equal to on both sides. And I'll pause here. All right. So here, when you're solving a system of linear equations, automatically assume that they cross until it's proven that they don't. So the first thing that you're going to do is isolate one of the variables in either one of the equations. Well, let's look at this one. Y is already on a side by itself. y is equal to this 3x right here. So then what you're going to do is rewrite the other equation and substitute 3x in for y. Okay, I'm going to repeat it one more time. Very first thing that you need to do is isolate one of those variables. Get x by itself or get y by itself. Here, y is already by itself. Y is equal to 3x. So you're going to take 3x and substitute it in for y in the other equation. So I rewrite this other equation, and I'm going to replace y with 3x. So this is going to be x plus 2 times 3x is equal to a negative 21. So that's what I have so far. Okay? So now I'm going to solve for x, and that's going to give me my x coordinate. So when I solve for x, this is x. This is going to be 2 times 3x, which is 6x, equals a negative 21. So here, I'm going to combine like terms. 1x plus 6x is 7x. Bring everything else down. Now to solve for x, I'm going to divide both sides by 7. So when I divide both sides by that positive 7, this gives me x is equal to a negative 3. Any questions about how I got x is equal to a negative 3? I'm going to pause to give you a chance to write. Okay, so here, my x coordinate is going to be a negative 3. And now I'm going to figure out what my y coordinate is. So I can use either equation I want. I'm not going to get the wrong answer no matter which equation I use unless I just don't substitute right or do some math wrong. So I'm going to use this first equation because it's easy. It's real short. So I'm going to, of course, use the easy one. So now, since I know what x is, I'm going to replace x with what it is, which is negative 3. So I have y is equal to x, 3 times negative 3. So this gives me a negative 9. So my y coordinate is negative 9. This is going to be my solution. Okay, so here we go. This one's number 5. This one's a little bit longer because as you notice, again, I'm going to assume, always assume, I told you this, assume until proven otherwise that these equations cross each other. The lines cross. So I'm going to go ahead and write this in. So that way I know I'm trying to find a value for x, and I'm trying to find an x coordinate and a y coordinate, okay? So in order to do that, just like I did before, the first thing I need to do is isolate one of the variables. They did it for me up here. They did not do it for me here. So I'm going to choose whether or not I'm going to isolate x or y. Here, I'm going to isolate x because look, x is almost by itself. And the other ones have numbers attached to it. So of course I'm going to choose the one where I know it's going to be less work. So I'm going to choose that first equation. Any questions about what I've said so far? If you're not sure about what I'm saying, then you need to ask questions, okay? All right, so let's go ahead and isolate x. Remember, it doesn't matter which one you decide you want to isolate. I'm just doing x because it's the easiest one to do. So to get x by itself, I'm going to subtract the 5y. This is gone now, and now x is completely by itself, which is what I wanted. These are not like terms, so please don't combine them, but bring them both down. Ms. Reyes, why did you put this one first? It's just my preference. You can write either one of them first. Okay, doesn't matter. It's not going to change anything as long as you keep the sign that's in front of it. So now I'm going to take this right here, just like I did up here, and I'm going to plug this into the other equation. So the other equation is the second one right here. So let's rewrite that second. And let's substitute negative 5y minus 3 in for x. So this is going to be 3 times, and this expression right here because this is what x is equal to. Okay. Now I'm going to bring everything else. I'm going to bring everything else down. All right. If you are lost, just let me know that you're lost. Okay. Now I'm solving for y. So all I'm doing is going to simplify and combine like terms. So here, when I simplify, distributive property, of course, is going to go first. We did that back in Unit 1. So we have 3 times a negative 5y, which is a negative 15y. 3 times a negative 3, which is negative 9. And bring everything else down. Okay. Now we're going to combine terms that are alike. Okay. So these terms are alike, so we're going to add these terms, combine these terms. So when we combine them, that gives us a negative 17y minus 9 equals 8. Okay. Now to get y by itself, you got to move this negative 9 first. So we're going to add 9 to both sides. Sorry, y'all. Excuse me. This is gone, and I'm left with negative 17y is equal to a positive 17. Okay. To get y by itself, I'm going to divide both sides by negative 17. Okay. This gives me y is equal to a negative 1. Okay. Y is equal to a negative 1. So my y coordinate is negative 1. Now all I have to do is figure out what x is. Use the easiest equation. And the easiest equation is this first one. But if you think the second one is easiest, you can use the second one. You're going to get the right answer as long as you do the math right. Plug in negative 1 for y. Plug the negative 1 there. 5 times negative 1. And this is going to give you x is equal to a negative 5 is equal to 8. To get x by itself, add 5 on both sides. And this gives me x is equal to 2, a positive 2. So my x coordinate is 2, and my y coordinate is negative 1. This is the solution. If you got lost anywhere, please let me know. I'm going to pause it here. Okay. All right, so this last one that I'm going to do with you is number 6. Okay. All right, so again, what you're doing is you're isolating one of the variables. Look, x is already isolated, so I'm going to use this. I'm going to substitute 4y into the other equation for x, because that's what x is equal to. So rewrite the other equation. Okay. And I'm going to replace x with 4y. So here I have 4, and x is 4y, and bring everything else down. Okay. I'm going to simplify this. So this gives me 16y minus 1y is equal to 75. 16y minus 1y is 15y. Bring everything else down. To isolate the variable y, I've got to get rid of this 15. Since this is multiplication, the opposite of multiplication is division. So I'm going to divide both sides by 15. This is going to give me y is equal to 5. Okay. So remember, my y coordinate is 5. So now all I got to do is figure out what x is. So I'm going to use the easiest equation again. That's going to be that first one. And I'm going to replace y with 5. So this gives me x is equal to 4 times 5. So x here is 20. Okay. Any questions about that? All right. Okay, Kaylee, are you okay with this? How you feeling? You said thumbs up. Maggie, how are you feeling? Are you okay with it? Thumbs up. Okay. Esmeralda, how are you feeling? Thumbs up. Leland, how are you feeling? Okay, good deal. Let's see. Can't see who this is on the bottom. Braden, how are you feeling? Good. Wisteria, how are you feeling? Good. What about you, Charles? How are you feeling about it? Okay. Don't be afraid to say that you don't understand something. That's anybody. Do not be afraid to say, I'm a little lost. It's okay, all right? Something new. Austin, how are you feeling? Okay, good deal. Jackson, how are you feeling about it? Okay, that's all right. All right. You got to get some more practice in before you can feel kind of comfortable about it, and that's okay. What about you? How are you feeling, Usher? You think it's okay? All right. Okay, Steven, what about you? How are you doing with this? If you have a loaner Okay. Chromebook, please turn it All into right. the bin in the hallway at this Think I time. Missed anybody. Oh, okay. We put if it's a solution or not a solution. Yes. Only time you put if it's a no solution, you need to say no solution. If it's infinitely many solution, you need to say infinitely many solution. And this is how you know that if you working out these equations and the variables cancel out and it looks something like this at the end, it's infinitely many. If you working this problem out and all of a sudden at the end it looks something like this where it's not equal to each other, this one is a no solution. It's going to be very obvious which one is which. Okay, Esmeralda, does that help a little bit? Okay. All right, guys, I'm going to go ahead. I'm going to let you go. If you have more questions, I need you to stay on the line. Please stay on the line if you have more questions.